Hello, friend. My name is Derek Carter, and in this video, we're going to look at convolutional networks, um, a slightly different topic. What we're looking at today is some ideas on how you can interpret what convolutional neural networks are actually learning. Okay, so this is a fundamental problem with machine learning models, that of interpretability, right? And many machine models are often criticized as being black box models. Okay, so by that people mean that it's not easy to peek inside of a big tensor of weights and things and figure out exactly what it is that your model is doing to make predictions, whether it's good or bad. Okay, but that's not necessarily true for convolutional neural networks because they are essentially visual, so you can actually peek inside. Okay, so anyway, let's go ahead and get started and talk about this some more. So as I started saying, so a fundamental problem with building, I would say many machine learning applications, not just computer vision, is that of interpretability. So deep learning models are black boxes, and machine learning models in general are black boxes. Okay, so that means that they learn representations that are difficult for humans to extract explanations for. Okay, so while this is true for lots of machine learning models, it is true. I would say it is true in general for neural network models. Okay, because having just a big weight, a big tensor of the weights, doesn't really give you an idea of how it's transforming those and coming up with, predictions that they make. But vision models especially are a little bit of an exception to this because what they are representing, in the filters on like a convolutional network, when you have a hierarchy of convolutions, is fundamentally visual, right? So we can actually extract those and see in ways that we can understand the representations of those kinds of convolutional layers, their representations of visual concepts. Okay. So we'll look at three techniques. I won't spend too much time on any of these, so we'll go through these kind of quickly. So the simplest idea is input an image and then visualize the activations, the output that come from the individual features of your convolution layers. Okay, so that's what this first technique is. Another way we can visualize Convnet filters is to find the image that will maximize the output activation of a filter. Okay, so this second example, we'll have some examples of using at the low level of using the tensor tape and gradients and things again. So some more practice on that. And finally, also in the last example, we'll show a method for visualizing heat maps in order to see the individual pixels in the image, how important or not important they were to making a decision about which class for a classification task we want to do. Okay. Okay, so like I said, the first one we'll look at visualizing the intermediate activations of our convolution filters. Is I think is relatively straightforward and easy to understand. So even if you knew kind of nothing about doing these sorts of trying to figure out how layers make their decisions, this would be one that a lot of people could obviously think of as something you could try. Okay, so we're gonna go back and use the convolutional network from scratch with data augmentation. The final best model that we had there on that was, if you remember, was the cats versus dogs data set. And we're going to use an input image that wasn't in the training of the test of the validation data. Okay, so we're just pulling this down from some Amazon bucket for us to use here. Here's then a utility function which will, given the image, will return an array of it, so as a numpy array, right? So this is what the picture looks like that we're using in this example, right? So a cat picture. So one thing we'll get a little bit of more practice with this example is using the introspection abilities of Keras, right? So we want to pull out, this only makes sense for like convolutional layers. I guess maybe max pooling layers. But so for example, for this model that we just pulled, that we had trained previously, we could go through it and just find all the layers that are of these types and make a list of those. So that's all we're doing here, okay? But we're doing more than that. So we're actually going to create a model that will take an input, the same inputs that we originally had for our model, but will output, the activation from all these layers. Okay, so this makes it very simple to do this kind of thing, right? So we feed in an input, and this input will just get fed to all these output layers. So then we can directly inspect the output activations for each individual filter that's being output from a convolution layer or a max pooling layer. So let's see how we use that. So if we just feed in our image tensor, so our NumPy array was formatted in that utility function to be the correct thing as an input to this little activation model that we created. We ask for the predictions. We get a set of 9 predictions. So there were actually 9 convolution and max pooling layers if we go back and look at our model here. So in a bit here, I think we'll show the summary of the model that we had. We'd actually already shown that before when we first loaded the model. So if you count that up, there was 9 separate convolution max pooling layers that we had here. So for example, if we wanted to look at the output activations for one particular filter, we could pick one of the layers. So we're just picking the very first layer. So this would be at the lowest level of the hierarchy. So if you remember, if I can go back to the summary of our model here, our first convolution layer was this one. So it ends up with a 178 by 178 shape, remember, because of the convolution, the sliding window. Since we didn't do any padding, it ends up clipping off the top, bottom, left, and right. Right, but the outputs from these 32 filters are output from this, and they're all going to be of that shape 178 by 178 here, right? So if you do this yourself, you might not get the same image here because the resulting model, what's being encoded in that channel, will differ. Okay, so it depends on the randomization of batches and things like that. But you should get something similar to this. So what's happening here is, the way you interpret this is that particular filter, we just picked one of the 32 feature maps or filters that we had that were being output from that channel, right? So it's anything that's bright is where it's responding highly, okay? So most likely it's an edge filter that's encoding things that have like an angle, something like that. So not completely horizontal or vertical, but something in this shape here, although it responded a bit there as well. But that's typically what these kinds of filters at the lowest levels will be doing. So they'll be like edge detectors of edges going in certain directions, or maybe curve detectors of curves with certain kinds of shape or things like that. Okay, with that, this visualization may or may not be too useful, but we can go ahead and just plot out every one of those activation maps for, again, this is all just in response to this one input picture that we have here, right? So for every layer, we're going to pull out the activations and display these in a big visualization here. So you should get something similar. So just a couple of things to note about this. So these layers are going in the same order in our network. So these things down here are going to be stuff at the bottom of the hierarchy, and things will get more and more abstract as you go further and further up the hierarchy. Okay, so things that are being encoded down here are a recognition of a kind of a high-level feature in some part of the image or not, whatever that feature ended up learning to kind of encode. Okay. So the first layer acts as a collection of various edge detectors, and at that stage, the activations retain most or almost of the information present in the initial picture, so you can still see the cats. So as you go deeper, you'll get things that you can kind of see are really like eyes, ears, noses, features like that. And you'll notice that for any activation that was all zeros, we just left it as blank. Okay, so this sparsity of activations will increase with the depth of the layer. Okay, so in the first layer, usually almost all the filters are activated, and following layers more and more will be blank. So the reason for that, so let's go back and look at some of this. So you notice that for these activations at the lowest level of the hierarchy, it should most of the time you'll see these, they'll be responding as edge detectors and things. Okay, so and usually edge detectors can be found all over the place, so you usually see not very many of these where the output is completely blank. Right? And then later on, as we get to middle stuff, probably some of these you'll be able to see, or maybe looking for eyes and ears and other kind of features. So they'll be highlighting stuff that looks kind of like features of cats or dogs. Well, in this case, it's a cat image, so we're only going to see responses to filters that probably learn cat specific. And that's kind of at the end, that's kind of why things will be much more sparse down here, because these things are going to be specific to features that might be useful for cats or dogs, right? So some of these are probably much more specific to dog-like things. So having two particular kinds of shapes of ears and, or something like that, right? So half of these are kind of not responding at all. And the other are going to be stuff that was probably more specific to one or the other class. So the second thing we'll look for visualizing the representations in convolutional network layers is a little bit more complex. So what we're basically going to do in the second method is try it. So instead of having an input image and seeing how the filters respond, we're going to build an image that will cause the maximum output activation for a particular filter. Okay, so in that way we can see a little bit more clearly sometimes exactly what kinds of features that filter is most highly responsive to, right? So the images that we build aren't real images. They're things that allow us to see exactly what it is that filter responds to. Okay? So for this one, we'll switch to the exception model. And I go through this one a little bit quicker here. So, there's some practice on, we have to build a loss function, right? So we want to build a loss function that maximizes the value of a given filter in a convolution layer. So it is an optimization problem. So we can use gradient. In this case, since we're trying to maximize, it's really a gradient ascent, right? So we want to go in the direction that causes the activation to get bigger and bigger until we get it as high as we possibly can, okay? So we'll go ahead and load one of a pre-trained model, an exception model that we have used before in the class here. And we don't need the top classification layer, so we'll chop off the top. So just as a reminder, here is kind of a list of all of the layers that are 2D convolutions or separable 2D convolutions. Okay, so in the second part, we're doing something similar to what we did before, although to build the optimization method, we're just going to show the example of doing it for one particular filter in one layer. So we build a feature extractor model, kind of similar like we did before, but we're just doing it for one particular layer. So in this case, we get that layer on our model, and we set its output as the output for our feature extractor. Okay, so kind of like we did before, we can pass in an input image, although we're using this exception model, so we have to pre-process this. We will be looking in more detail at the exception in the next video here, or if you haven't seen that video yet. But kind of similar like we did before, if we passed in like the cat picture again, we would get the output activations from this particular convolutional, separable convolutional that we did here. So in this case, it's outputting 44 by 44 with 256 feature maps. So next is the trickier part here, but we need a loss function so we can set up a optimization using gradient descent. So using the gradient tape from TensorFlow, like we've seen some examples before. Right? Loss function shouldn't be too tough to understand, right? So if we pass in an image and a particular index for the filter, and we are reusing that feature extractor, right? So right now it's hard coded to use the particular layer here. So if we wanted to use a different feature in a different layer, we'd have to redo these cells, select a different layer here. But some details, edge effects can sometimes ruin this method. So we'll just clip off 2 pixels from top, bottom, left, and right from the activations. But all we're doing is calculating the mean activation. So again, the output of the activation is going to be a value 0 to 1 over the, in this case, 44 by 44 pixels for that one index that we're selecting. Right? So we just take the mean of those. Right? So this isn't too different from the example that we showed before, or one of the previous assignments where you had to implement a gradient descent by hand, right? So using the TensorFlow gradient tape, if we give it inside of the tape context, if we give it an image and compute the loss, it will keep track of the gradients for us that we need. Okay, so then given the gradients from the tape here, all we have to do is update the pixels in the image in order to go ascend, to go towards a larger gradient, right? So instead of doing a minus equals, we do a plus equals time of a linear rate times the gradient. Okay, so similar to what you saw before, but we're doing maximization instead of minimization for our optimization. Okay. So I mean, that's really it. We have all the pieces that we kind of need. So this function here is going to perform a gradient ascent for 30 iterations. So we might have to adjust the learning rate for different layers or things like that. But we just repeatedly call the previous method for a fixed number of iterations here. And have it improve. We start off with just initially a random image. Okay, so the image is just all random pixels with a value between 0.4 and 0.6. Okay, so we're using images that have already been normalized to values with 0 to 1 pixel range. So these are all kind of close to the middle of the range for the input RGB channels. Okay, so we need a utility function to actually turn the resulting image from this process into something that we can display. So that's all that this does here with a little bit of normalization and clipping here. Okay, so anyway, so let's show it. So this is necessary in order to denormalize some of the stuff that was done in the pre-processing. So if we call that to do our maximization, optimization, and then show the result, we'll see for that particular filter in that particular layer what we're getting. Okay, so usually you'll get things like this for lower layer levels. Okay, so so usually the things that we describe as edge detectors will be, I mean, it'll look a little bit kind of wavy on here, but they're maximally within whatever patch they're looking at, looking for things. This is mostly kind of relatively horizontal lines here. So sometimes it will be more curvy, or be more vertical. Those kinds of ranges, depending on the ones that you look at. So from that, if we want to, we could generate these images that maximally activate the filter for like all the filters in this layer. So that's what this next block does here. So if you look at that image, you'll get something like this. And we can do it for any layer that we want. If we want to do it for a different layer, we'd have to go back up there and change the layer name and rerun those cells to be doing it for a different specific layer here. So these are some of the layers that the textbook showed, right? So for the lower layers, you get stuff. It looks wavy like this. These are kind of the edge detector layers. And if you look at the higher levels, you'll begin to pick out that, again, that these are doing things like features like maybe eyes and nose and stuff. So usually these kinds of patterns at the higher levels of the hierarchy, you can begin to see some things like that. That those filters are maximally being sensitive to, right? So, and kind of remember that these end up being really small patches. So the very first layers are going to be looking at like just a 3x3 window. But because we're doing max pooling and stuff, the things down here are going to be looking over much bigger windows, like maybe 32x32 or 64x64, right? So these will end up being usually like a little thing on here, the typical, say, maybe eye size of the eyes or the cast of the dogs in the original image. Okay. Okay, and then finally, let's look at the third technique. So this is trying to get a sense of how individual pixels in the final image or the channels that are looking at those pixels, how important they are to determining which class was going to be output as the predicted class from a classifier. Okay, so so this has name class activation maps from the paper that first showed doing this. So this class activation CAM is a 2D grid of scores associated with a specific output class. Okay, so it indicates basically how important each location is with respect to the class under consideration. Okay, so to do this, we're going to input an image that has a particular class that the model is maybe getting right or wrong, and then apply this CAM here. So basically, we take the feature map, the filter outputs of a convolution layer, given an input image, and we're going to weigh every channel for those those feature channels, those filters, by the gradient of the class with respect to that channel. Okay, so just intuitively, a way to understand that is to imagine that you're weighting a spatial map of how intensely that input image activates these different channels, these different filters on a particular convolution layer. So that gives you some idea of how important each channel is with regard to the class that's being represented in the image. Okay, so you don't have to understand all that, but basically this is another good example. We have to do a loss function again and calculate gradients. So this one we're using the exception again, but since we need to know the final classification, we don't want to chop the head off. Okay, so we're keeping the full model this time with the convolution hierarchy and the head, the classifier at the top. So for this one, again, for the ImageNet, it did 1 of 1,000 classifiers. So just kind of quickly, and again, we're using an image that isn't part of the ImageNet data here. So we're using this image, although the actual image, this is after pre-processing, so it's actually resized it, and the color looks a little bit off here, but this is what happened after the standard pre-processing. But you can look, so if you're not familiar with the ImageNet task that exception does, so we can decode the predictions here. So it basically there's 1,000 output classes, right? So the output from the classifier from this model is a softmax. So you should know the usual thing is done for doing a multi-class classification. These are the top 3, right? So it's given on the softmax function, it's given 86% chance that it's an African elephant, which is correct, and then a little bit of a chance that it's some other type of elephants, tusker or Indian elephants, right? So among the 1,000, for example, that ends up being the class 386 or index 386 in the predictions of the one that had that 86% estimate on the final softmax output here. Okay. Okay, so just to show you how this works, so we have to do some similar things like we did before to create a model. In this case, we're looking at the last convolutional layer to do this heat map that we create here. and we want to also add on the layers that do the classification. Okay, so the final classifier model here has just basically the last layer, and these layers, the final layers that we're doing the final predictions for our model here. Okay, so basically I won't go into details, but if you put in an image, you can get the gradients out of the gradient tape, and these basically give us a measure for each of the pixels in the output filter, their importance. Okay, so we have to do a little bit of processing then to superimpose that over the original model. So we can get a heat map. This is what the heat map looks like. So this final filter only had 8 by 8, I think. So it was only like a 64. Sorry, it was 8 by 8 size for this particular one filter that we're looking at here. This is the pooled. So this is the pooled gradients over all of however many output filters were coming in from this. But the shape was like an 8 by 8, I believe here. So we have to enlarge that and reimpose it. So that's what this code is doing here. So we'll get an image like this. Okay. So basically, to interpret this, again, the red, the hot is the areas that were most important that to contributing to getting the output for that African elephant, the 386 index. So these areas were the most important for getting that score to be the hot, the value that we end up getting. Right? So the speculation in the textbook is that it's maybe this is getting in. I mean, the elephant, the baby elephant, obviously, but getting in on the ear shape, which is important for differentiating between African versus non-African elephants. So that's it. So in summary, just a summary about the stuff we talked about in this video. The representation that machine learning models learn are black boxes, so they're not always easy to figure out what they're doing, but it's different really for convolutional layers and convnets because they are essentially representing visual information. Okay, so they're the opposite of a black box. Okay, so these were just 3 example techniques. So there's more sophisticated ones, but definitely, if you do any work with convolutional networks, it is useful at least to do the first technique or two, as early in your process to visualize what the filters you're actually learning on your outputs. All right, so that's it for this video. I hope that was useful for you, and I hope to see you again in the next video.